It's often said that the best geologists are the ones who have seen the most rocks. Similarly, of course, the best interpretation geophysicists are the ones who have seen and studied the most seismic sections. We're all a hostage of our own experience and vision. One of the key challenges that we face in the future is how we can effectively explore, develop, produce from smaller fields than our predecessors had the fortune to work with. To do that, we need to be cleverer. One of the things that BP has made a strong commitment to is to increase the rate of growth of an individual's knowledge, and our commitment to training is a part of that. When we study seismic sections like this, or even geology and outcrop, we can only see the end point of a tectonic process. We can't see how the structure evolved, and what's the genetic significance of the various features of it. If we can improve our understanding of how and why structures like this form, and appreciate the significance of complex folding and faulting that we see in the data, then we'll be able to expand our minds outside the limit of the data itself. Mathematical modelling provides one route of doing this, but most of us have problems in visualizing the output from complex algorithmic computations. So what we needed was to find a way in which we could illustrate the processes going on in a way that all the technical professionals working in our industry could understand and assimilate. Physical modelling of structures was first attempted a century ago, when H.E. Cadell used clay in an attempt to reproduce the thrusts of the Scottish Highlands. Since then, many attempts have been made, with varying degrees of success. A new era of modelling was started in 1984 in Royal Holloway and Bedford New College, supported from its inception by BP, and the results form the basis of this film. The man who has led the project from day one is Dr. Ken McClay.
In order to produce dynamic models of extension in sedimentary basins, we must use model materials which accurately scale the brittle deformation of sedimentary rocks in the upper 10 kilometres of the crust. Such materials must have a linear Navier-Coulomb rheology and include dry quartz sand, dry mica, or dry clay. They are weakly cohesive to cohesionless and accurately simulate the brittle deformation of sedimentary rocks. This is an example of a sliced model produced in a deformation apparatus such as this. The rig is extremely simple. It consists of two end walls, one fixed to the base of the deformation rig. The movable end wall is attached to a movable base plate and attached to a movable plastic membrane. We have two glass sidewalls by which we can observe the progressive evolution of the structures, and in this case, a fixed footwall geometry of a listric fault. Deformation is achieved by moving the end wall such that the moving plastic sheet translates the model over the fixed footwall geometry. This deformation is achieved by means of a motor-driven worm screw, which gives a displacement rate of about 3 × 10⁻⁴ per second. We can alter many variables in the apparatus. We can change the footwall geometry such that we have a ramp flat listric geometry. Or if we want to simulate deformation above a uniformly extending detachment, we use a rubber sheet. We build the models in here. A typical model is 30 centimetres long, 20 centimetres wide, and 10 centimetres deep. 10 centimetres of model represents between 1 and 10 kilometres of sedimentary rocks in the crust. What do we make our models out of? We typically use dry quartz sand, either undyed or dyed various colours. Quartz sand has a grain size of 300 microns and an internal angle of friction of 31 degrees, which simulates the deformation of isotropic sedimentary rocks. If we want to introduce an isotropy, we use microflakes between the sand layers. If we want to introduce competency contrast, we use clay or sand-clay mixtures. Building the models is extremely simple. We carefully sieve sand into the model. Once we have constructed the model out of alternating layers of coloured sand to the top of the apparatus, then we can extend it.
The unique quality of this work is that the models allow the researcher to see how structures develop. Ken McClay uses still photography and a time-lapse filming technique to record the development of each model. Individual parts of the model are photographed before the extension starts. These can be compared with stills from various stages of extension. Then, the time-lapse 16mm film camera is started.
Okay, Scotty. 3, 2, 1, go.
At 1 frame per second, this speeds up the development of the model in film terms by a factor of 25. The results from Ken McClay's filming form the core of this program. As the layers of sediment are extended, new sin-rift sediments are added. Here, the red sand. The models are always filled to the top to simulate continuous sin-rift sedimentation. This program features the development of 5 extensional models, all with different geometries. The first model is a simple listric fault. As extension begins, the hanging wall is pulled away from the footwall. It accommodates to the shape of the main fault surface. The initial deformation is not by faulting, but is by ductile change of shape, which gives a depression immediately adjacent to the major fault. As the extension continues, secondary faults develop. These form in the crest of the rollover, in the deformed section of the hanging wall. The outer part of the arc of that rollover is stretched more than the inner, and the faults form in response to arc stretching. This structure, called a crestal collapse graben, is bounded by 2 types of fault. Synthetic faults dip in the same direction as the main controlling fault, start steep, and subsequently rotate to become convex upwards. Antithetic faults dip in the opposite direction and tend to remain planar. Extension and displacement on all crestal collapse faults dies out downwards. As the faults develop in the crestal collapse graben, new faults are initiated closer to the main controlling fault. Here, there is an original synthetic fault that has been rotated towards the horizontal, and a new steep fault which is developing in its footwall. Steeply dipping synthetic faults continue to develop in sequence towards the major controlling fault. Note how the regional dip and elevation of the hanging wall remains the same as that of the footwall. This is because the fault plane itself has become flat at depth. Remember, in these experiments, the void in the hanging wall is constantly being filled to the top. Sedimentation exactly keeps pace with the void created by extension. If the basin were starved, the resulting geometry of the sin-rift sediments would be different. Frequently on seismic data, the fault plane is not seen clearly enough to be confident of its shape. If we can see the geometry of the hanging wall strata, we are able to make analogies with the experimental results. These demonstrate that, if the elevation and dip of the undeformed hanging wall strata is the same as that of the footwall to the main controlling fault, then the fault must flatten at depth into a horizontal detachment. This seismic example shows a half graben and a crestal collapse graben. By analogy with the experimental results, we can predict that these are a genetically linked pair of basins, both generated by a major controlling fault that is listric in shape. The difference between Model 2 and Model 1 is that the basal detachment of the controlling fault dips. This causes the hanging wall to be lowered below regional. As before, a preliminary deformation of the hanging wall develops before the appearance of any secondary faults. A depression forms against the main controlling fault, which is progressively infilled by the red and white syn-rift deposits. As the extension increases, the development of a crestal collapse graben becomes clear. The synthetic fault which bounds it rotates and becomes flatter upwards. The planar antithetic bounding fault stays more or less in the same orientation. A secondary synthetic fault develops. The orientation of that fault changes as it passes upwards into the syn-rift. A secondary crestal collapse graben develops on the right-hand side of the model. This is bounded by synthetic faults, which steepen downwards, and antithetic faults, one of which is planar, the other listric. As the model evolves, both grabens continue to develop, and between them a Horst block remains relatively unrotated as a high. Increased extension results in flattening of the synthetic faults with the rotation of the central section of those fault planes. Those faults then propagate upwards into the syn-rift fill. Here they form an imbricate fan of listric fault planes which steepen upwards. This results in an apparent disharmony between the structures of the syn-rift fill and the pre-rift below. In the pre-rift sequence, crestal collapse grabens develop due to arc stretching. The faults do not continue down to the basal detachment, and there is an unfaulted segment immediately adjacent to the main controlling fault. This sector, however, is highly rotated with the dip of approximately 70 degrees. At the top of the pre-rift and base of the syn-rift, the dip is almost perpendicular to the main controlling fault. Rotations as strong as this have to be associated with listric faults in areas of low extension. This seismic line displays a comparable geometry to the kind of structure modelled in the experiment. Above an inclined basal detachment, a series of listric faults has gradually lowered the hanging wall below regional elevation. Very large extension has produced rotated blocks, with high-angle dips against the basal detachment and sedimentary growth above each rollover. New faults develop in the syn-rift as the extension proceeds, but their orientation is closer to the most common orientation of extensional faults in undeformed materials, at approximately 60 degrees. The geometry therefore shows a change from a steep dip deep in the pre-rift section to a gentle dip in the upper part of the pre-rift and the lower part of the syn-rift. There is a steep dip once again in the upper part of the syn-rift section. The whole shape is sigmoidal. I discussed the implications of these models with Ken McClay and Chief Geologist Ian Van. What sort of scale are you actually simulating here, do you think? I mean, when we're looking at this, should we be thinking of the North Sea, half the North Sea, or an individual prospect within the North Sea? Or?
I think in this scale, when we have a single listric fault, we're looking at a scale of between 1 and 10 to 20 kilometres. So we're actually looking at an individual fault block and what happens in the hanging wall to that fault as it evolves.
Interesting thing about it, of course, is the way those, particularly this fault, develops, which is so clear in the movie there. It starts off essentially plain and non-rotational. And what it seems to be happening here is becoming a detachment surface. There's tremendous complexity underneath that surface and apparent simplicity above. For obviously anybody interpreting a seismic section, it's going to be a horrific problem, because there's no continuity of faults through that surface.
No, that's right.
And this is a feature we find in many of the models, that once you get to about 50% extension, you develop a listric fan in the upper synrift sequence and a complex array of often convex downwards faults in the pre-rift.
Have you done much work on the changing cutoff angles? For example, when we talk about interpretational models here, we might want to use a consistent cutoff angle during deformation. Is that real or not?
Well, if we look at this model, we can see that in the synrift listric fans, up on these small faults in here, the cutoff angle is consistently between 60 and 65 degrees. But with increased extension, of course, the faults start to rotate, and so they become, in fact, listric at depth and flatten out. If you actually do a strain analysis, you see that, in fact, the fault cutoff angle with respect to the bedding plane does, in fact, decrease, so they go around to around about an average of 45 degrees. So one of the important points I think we can see from many of these model experiments is that as the faults develop, the cutoff angle changes due to internal strain within the fault box.
This is obviously useful as a guide to interpretation of real data, but we really need to know just how sensitive these models are to a change in boundary conditions.
I think the important point is that you can see basic geometries, and if you alter this pattern of geometries, then you get different structures. If we take the second of our listric fault models, which is this one here, we can see that by changing, in this case, the dip of the basal detachment, so in this case it's horizontal, here we have a 10-degree tilt, downslope. We have a slight change in the overall pattern, although in this case it's very similar, except we've gone to 100% extension, not 50% as in this case. We still have a listric fan, but in this case it's much better developed. Crestal collapse features which migrate towards the major detachment and migrate up section in the hanging wall, so that at the later stages of deformation they're concentrated in this upper section in here.
Yeah, that development of this panel of unfaulted rocks, interesting, isn't it? I mean, you see the first attempts of it at the start of it in the previous model, but here it's completely developed, and you almost get the impression that the rocks of the synrift here are deforming differently from the pre-rift.
Yeah, they appear different, but in fact, this is basically homogeneous isotropic sand. The colours are just layers. So that if we look at this panel of rocks, as the displacement increases, then they become rotated and become vertical almost to the basal detachment. I think it's really a function of where the hanging wall is in respect to the geometry of this detachment. With greater strain, greater extension, then we get this development of panel of underformed rocks, and all of the deformation starts concentrating in the synrift sequence.
These models all display crossing faults resulting in grabens above Horst, which is something we've seen in places like Holland or Dorset. Is that a feature of your models?
For example, in here, we have one in this position here. It's a fact that, particularly in the modelling materials, it has very little memory. Yeah. So you can deform once, and then you can deform it in another orientation again, so faults can cross. They need not, in fact, be conjugate. You can form at different times and produce this sort of structure. And you do see it on some seismic sections. Northwest Shelf of Australia is another example where you get this graben above Horst type structure.
There's another thing that always confuses me and other individuals, perhaps, was the expectation of what would happen as we approach the detachment. You never see that, of course, in the seismic data. It's all lost in the noise, but by the time you get to the detachment surface, it's very clear on these models that faults start to die out rather far above that basal detachment.
The problem is, of course, in this region here, is that displacement is small, so we don't see the effect on the layering. This is, of course, a geometric necessity of the model, and this is, in fact, perhaps a limitation of the models. In fact, that you have to have faults dying out towards this basal detachment. Yet, when you look at the strain analysis, you see that this, of course, is a shear zone, and there is a zone of uniform strain, which I think realistically models what actually happens in the crust.
Well, the interesting thing about this model, of course, is the prevalence of very steep faults. Again, these things curving downwards to have 90-degree or even greater intersection angles.
Well, in all of the Listric models, what we see in typical cases is the antithetic faults remain planar and they migrate progressively towards the main detachment. Yep. The synthetic faults start off being planar but very quickly rotate so that they become steep in the lower portions, flat in the upper portions, and then migrate into a Listric fan in the synrift. And that is a feature we see on many of the models, whether we have the same materials, the same detachment geometries, or we alter them. This feature is a common parameter.
Model 3 is a variation on the Listric model, with a detachment surface which has a ramp flat shape. Initial stages of extension are similar to previous models, with a ductile shape change in the hanging wall. A half-graben develops against the main fault and a syncline over the steep ramp section. The hanging wall in the extreme right of the model is not lowered because the basal detachment is horizontal and results in preservation of the regional elevation. A crestal collapse graben forms over the flat sector at the left-hand end. The synthetic bounding fault of this graben flattens upwards. At the extreme right end of the model, an antithetic fault develops and heads towards the point at which the basal detachment changes from being steep to being flat. This develops into another crestal collapse graben and results in the progressive change in shape of the antithetic fault from being perfectly planar to being slightly Listric. The sequence of fault development within this right-hand graben is progressive towards the major detachment surface. The crestal collapse graben does not continue to the basal detachment, but dies out about halfway down the model. The early formed fault on the extreme right, which is now inactive, has reached the basal detachment. As the extension proceeds, a highly rotated sector develops over the flat section of the basal detachment. To the right of this, the ramp syncline continues to develop. In the right-hand crestal graben, the more active faults occur on the left-hand side of the structure. The left crestal collapse graben is being pulled over the ramp sector of the basal detachment. The displacement on the original synthetic fault is gradually increasing, and above, in the synrift section, fold structures are starting to develop. There is a well-developed asymmetry and large displacement of the synthetic border fault of the crestal graben as it is gradually pulled over the steep sector of the ramp. Within the right-hand graben, there is a complicated intersecting system of synthetic and antithetic faults. At the top of the well-developed but fault-free syncline, we can see the development of lensoid geometry within the synrift. This seismic example shows a half-graben against the main controlling fault and, to the right, a major syncline above a ramp segment of the fault plane. These geometrical features within the hanging wall are predicted by the analogue modelling of ramp flat fault profiles.
The astounding thing, Ken, about these models, we start to see all these compressional features, essentially thrust faults, although these are dominantly folds, I guess. Is this invariably the case, or are we looking here at something to do with the introduction of mica into the model?
No, if we actually look at the geometries of deformation, we have this panel moving in a band this way. This panel is dropping down faster than this section. So in fact we have a zone of reverse faulting where in fact the footwall is moving down with respect to the hanging wall. In addition, we have this accentuation of the folding of the rollover anticline as it goes over the round. We find these in all the models. The mica, in fact, reduces the amount of reverse faulting in here.
Again, those are features that one would never interpret seismically, and we know within an extensional regime, hence you can't have reverse faults. There are other fantastic things about this particular model, which are kind of pitfalls of seismic interpretation, if you like. Notice here, the geometry of these beds is precisely that of an aggradational progradational system.
Absolutely.
And yet, here we're always filling to base level. It's a tectonic simulation of a entirely depositional process.
What I have as a question for you is, have you seen seismic examples of this sort of structure?
There's certain similarities between this and the regional seismic from the Gulf of Mexico, but whether one has the courage to interpret everything one sees here in a seismic line is a different question. Model 4 is a uniform extension over a stretched rubber sheet. Initially, a series of extensional faults develop with small displacements. Continued extension results in minor rotation of these structures. The progressive development of rotated fault blocks follows, with an increasing number of faults developing. As the displacement increases on individual faults, there is a rotation of both the fault and the fault block. It's interesting to point out that the faults steepen towards the top of the pre-rift, and that rotation of the domino fault block is less pronounced in the upper part of the pre-rift. In the syn-rift section, the faults generate upwards at an angle of about 60 degrees. They then rotate flatter, so there's an element of lustricity which results in the younger part of the syn-rift section displaying the steeper faults. Many extensional basins show domino faults, where the degree of rotation is proportional to the degree of extension. This domino style of structure is displayed on the seismic line by a series of large fault blocks. There is, however, a limit to the amount of rotation on an individual fault set. In other areas, these early faults have been observed rotated to very shallow angles. Eventually, these faults lock and become inactive, and a new set is developed which cut through the original low-angle ones. Extension is taken up on these new faults, and they, in turn, rotate. In very extended basins, complicated systems of fault sets develop. Most geologists now think that crustal scale faults approximate to dominoes, and that they may also occur on a smaller scale. Model 4 was pulled from one side, but Model 5 was pulled from both sides symmetrically. Initially, there is ductile thinning, giving a shallow depression in the centre of the model. Two planar faults then develop, which dip in opposite directions at each end of the model. The next faults to develop are synthetic planar faults in the hanging walls of the first formed structures. Now, in the centre of the stretched area, two initially antithetic faults start to develop on either side of a central Horst block. These eventually become the major faults of the system, the bounding faults of an asymmetric half-graben to the left and a more symmetric graben to the right. The two asymmetrical graben structures on either side of a central Horst now develop in different fashions. On the left-hand side, there is the development of a whole array of fault blocks, which are rotating as domino structures. On the right-hand side, the graben develops with a leftward-dipping listric fault, which merges with the original bounding fault of the Horst block and becomes the dominant fault in that system. The variations seen in the geometry of the two grabens may be a guide to the range of structures which occur in nature. The geometry of structures in the seismic line are comparable with those seen in the models. Planar, near-vertical faults divide the basin into a series of asymmetric half-grabens, separated by more stable, horst-like blocks.
This sort of deformation, I think, is characteristic of particular terrains like the basin and range, where you have an uplifted extensional origin and you allow rotation to develop in the hanging wall, and there's no constraints because you basically have erosion. When you have a sedimentary basin subsiding and the extension is confined to a certain zone, then this sort of model applies. But as you said, the symmetrical graben structures seem to be unusual in reality. They may contrast perhaps with this model here, which is a similar model, except in this case we have an asymmetric extension, and we've pulled the hanging wall away to the left here, and we've produced a characteristic asymmetric graben pattern like this.
Yeah, I mean, this is the kind of thing that we do see. The previous model is not. Yet, as you say, the previous model has its supporters in the literature at least. It seems to me, in fact, that asymmetry is the absolute characteristic of all graben systems. The other nice thing, of course, about this model and your analogue there is perhaps a tremendous database has been built up in the Basin and Range province. Shouldn't be used all that blindly when you're looking at graben systems as a whole. The Basin and Range is anomalous.
These domino structures are not the norm. In the models, we can only see them develop where we, in a sequence like this, where we have a free surface that allows the rotation to develop. If we have a constrained rotation, then these bounding faults, as in these sorts of models, control the amount of rotation, and hence you get these graben features like this.
This has been a brief introduction to the wide variety of structural models which are being studied at Royal Holloway and Bedford New College. Studying both the evolution of the structure and the final model adds new insight to the processes occurring within the Earth. This provides an extra dimension to our understanding of the structural complexity of the real world and how to interpret it.